is to finish with section E, the inclusion and exclusion principle. If possible, which I don't think so, get started with graphs. Otherwise, we'll just start on Thursday. Okay? So we'll need the graph theory book, and essentially for everything else we're going to do except for section E, everything else we're going to do between now and the next exam. And then we'll go back and actually we'll do a combination of the two books for the third part of the semester. All right? Okay, so let me share. I hope you had a really good spring break. I tried not to do as much from, the usual, my usual work with my classes and my students. I was trying to finish a paper. I'm almost done, but I try not to get distracted. So I'm happy about that. I'm almost done with that. But then I started grading your exam yesterday. And so I should have it done quite soon. I have a rubric, so that will give you an idea if you want to kind of, if you're anxious about it. We'll go over the solutions today, and it should be ready in a few days. Okay? I'm about a fourth of the way. So it took me, I graded like 9 or 10 exams yesterday. So I'm hoping that, in the next few days, it will be ready. Okay, so here's a copy of the exam. We'll go very quickly over every single question, and then just let me know, stop me if you need something, if you have a question, and then we'll go to section E. So the first question was, I will say closer to section A in the book. So this is essentially, most of it is permutations. So these are rearrangements of the word enjoy. You have 5 letters. So these are just permutations. So 5 factorial. The word muffin, this is 6 letters, but there are 2 F's. So we have to divide by 2 factorial. And then in blueberry, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. And we have, let's see, we have B, 2 B's, then we have L, U, 2 E's, and 2 R's. And therefore we need to divide by 2 factorial, 2 factorial, 2 factorial. Then for the word bananas, having all the A's together, we just glue the A's. And so now we have, 5 symbols instead of letters. Now we have the AAA as a single symbol. And then we have B, 2 N's, and an S. So it's 5 symbols, 2 N's. 2 of them are N. So we have to still divide by 2 factorial. So this is 5 factorial over 2 factorial. And then if there are 3 A's, if the 3 A's are separated, so there are 2 things, well, there are more than 2 things that you can do here. So one of the most typical methods is to first rearrange all the other letters. So B, N, N, S, and this takes 4 factorial over 2 factorial ways. And then choose 3 of the 5 gaps for the A's. So I have, some permutation of B, N, and S. They don't have to be in this order. That's why we're multiplying times it for 4 factorial over 2 factorial. And so we just choose 3 of these for the A's. I have 1A here, 1A there, and 1A there, and then I'm sure that they're completely separate. So your answer here is 4 factorial over 2 factorial times 5 choose 3. Mm-hmm. That's one possibility. So this is a completely different answer. You can use, which now we call the inclusion-exclusion principle, and that's one of the main reasons why I actually want to go over this answer. We didn't call it that before, but we used this idea many, many times, which is, the complement idea and a little bit more. So we can consider all the words. So that would be 7. So we have 7 letters. 3 of them are A's, and 2 of them are N's. So these are all the rearrangements. I'm dividing by the 3 factorial and the 2 factorial because I have 3 A's and 2 N's. And then I'm going to subtract. I want the ones where the A's are separated. So I'm going to subtract the ones where I have A's that are together. But I need to be careful here. So one thing you can do is you can put 2 A's together, and then you have another A, and then you have all the other letters. So B, N, M, and S, right? So this is 6 symbols, and only 2 of them are equal. So that would be 6 factorial over 2 factorial. Okay? And so the only issue here, so this is like the complement idea, right? I haven't finished this a little bit. So I have all the words, I subtract the ones that I don't want, and in the ones that I don't want, I have at least 2 A's together. The problem is that every time that in a word I have that double A and the A together, that's a word that has 3 A's actually all together. And it's counted twice because I can have the A, or I can have the A. And as words, they're going to look exactly the same, but I'm subtracting them twice. So, and I only need to subtract them once. So I need to make up for that. So I need to add them again. And those words are the ones that we actually counted in the previous part. So these ones are the ones that have 3 A's all together. And then, the other. So that's another possibility. And this really is inclusion exclusion. It's like, we can probably even set it up with the notation that we had before for inclusion exclusion, but we'll go back to that section. Okay? But you don't really need it. Okay. So that's problem 1. Any questions? Okay. So for part 2, this is more like, combinations with repetition. This is more like from section B of the book. You have 3 varieties of muffins: chocolate chip, banana nut, and blueberry. How many can you purchase? 2 dozen muffins, or a dozen muffins if you get at least 2 of each kind. So, you can use the table, the distribution table. That's one possibility. But really, I think the best way to think about this one is as solutions to an equation. So x1 plus x2 plus x3, which is, the chocolate chip, how many chocolate chip, how many banana, how many blueberry, and you want to buy 24 because it's 2 dozen. And in this one, you don't have any restrictions. So you just have that the xi's are greater than or equal to 0. And of course, integers. So that. Mm-hmm. And so the answer to this one is 24 plus 2 separators choose the plus signs, right? So 26, choose 2. And then for the other part, it's the same idea, but this time you only have a dozen muffins. So the sum has to be 12. And also, you need to have at least 2 of each. And these are integers, right? So we learned how to do this. We need to add up to 12. But since we're using 2 of each, we subtract those 2. So 2 minus 2 times 3, because we kind of, give me 2 chocolate, 2 banana, and 2 blueberry, and then we take care of the rest. So now we only need to buy 6, right? So this is 12 minus 2 times 3, that's the 6. We need to buy 6, and it's the same idea as in the previous question. But we even have a formula for this, with the sum of AIs, and that's what we're subtracting, which were the lower bounds for each of the exits. Okay. And that's program 2. Any questions? All right. So I'll upload this right after class. Which reminds me, sorry, I just sent a message from Canvas. I have to move my office hours a little bit later because I usually don't have enough time in between this class and the office hours. So instead of 1:30, starting today, I'll start office hours at 2. So I just sent a message from Canvas, but before I forget, let me tell you in case you were planning on going. Okay. So problem number 3, this distributions, and in fact, this is identical muffins into identical boxes. So these are partitions, numerical partitions. So, So as a general explanation to this problem, we have identical balls, or the equivalent, right? To identical boxes. And so my M, if you want to use the table, is 36, and the N is 3, and we have certain conditions. But for all of this, we're going to have numerical partitions, the function P, or some of its variants. Okay, so in the first one, there can be empty boxes, so this is the equivalent to no restrictions. And so this is just P36 3 plus, that's if I don't have empty boxes, if I have one empty box, and if I have 2 empty boxes. And then in part B, it's just no empty boxes, so that shows the first part of my answer in part A. And then in part C, there are at least 10 muffins in each box. Well, for this one, because I specified somehow, some version of a specified number of balls per box. Then I actually need to have the partitions that are allowed here. So the possible partitions where all the parts are greater than or equal to 10. Well, actually, no, you know what? Sorry, guys. I don't really need this. I could do that if I wanted to do this by hand, and it's actually small enough that we can do this by hand. But instead of doing this, I'm just going to use the special notation that we have for So this 10 is the, at least 10 muffins in each box. So that's a special, so instead of explaining in words, I can just use the notation that we have for that, right? And the only thing is that according to the instructions, I need to reduce this to regular partitions. And so I have this, which is the same as doing 36 minus 9 times 3. And I'll explain. Well, this is one of the formulas that we have in the distributions table. We are just subtracting the 10 minus 1. This 9 is 10 minus 1. And essentially what's happening is that we're placing 9 muffins in each box to start with, and then we just count the rest of the partitions. Give me 1 second. Sorry, guys. Okay, so this we have the formula. You don't have to explain it, but really, what is happening is that you want to have 36 identical muffins into the 3 boxes, so you can just put 10 in each box and then take care of the rest. That's what this minus 9 times actually 9 in each box, and then solve the rest of the problem. And why 9 and not 10? Because in the partitions, we ask for each of the parts to be at least 1. So, I just put 10 so that I could still have a 1. If I just subtract 9 so that I can still have a 1 in a box. If I subtract 10, then I'm making actually all the parts greater than or equal to 11. So anyways, that's the explanation, but this is the formula that you have in the table, and that's all you really needed. So this is 36 minus 27, P93. And then there are different number of muffins in each box, and at least 10 muffins in each box. Well, this one, there are 2 things that you can do. In this one, I think the best thing you can do is do it by hand. It's probably the easiest way. So they need to be different, and they need to be at least 10. And they need to add up to 36, right? So I can have 10, and then the next part, the smallest possible part is 10. And then the next one cannot be 10 because they need to be different. So let's say 11, and they need to add up to 36. So this is one partition. Mm-hmm. Then another partition, I just fix the 10 and see what other possibilities I have for the sum for the other 2. So 12 and 13, 12 and 14. That's a sum of 36. And then the next one will be 13 and 13, right? 10, 13, 13, but they all need to be different, so I don't count it. And so now I change the 10 to 11. And so the next one can be at least 12 because they need to be different. And then the next one is forced to be 13. And I cannot make that sum of 25 in any other way with numbers that are greater than or equal to 12. So that's it. So your answer is 3. Just these 3. Okay. So I think that's the best way to do it. Another way that you can do it, if you're looking for an alternative, is we already solved the one for having at least 10 muffins in each box. Mm-hmm. So if you wanted to make these with the additional condition that they are different, and if you understand that what we did here was simply taking care of 9 of the muffins first, 9 per box, 27 of the muffins first, this actually tells you that the answer to this question is just the same answer as before with the start to make all the parts different. Okay, so this actually corresponds to the previous answer, but making all the partitions different. So that also works if you want to. Mm-hmm. And according to our formulas, this is 9 partitions of 9 minus 3 choose 2. This is one of the formulas that we had in that in the distributions table. So this is P63, which actually is 3. So, there is a lot more thought behind this one. There's a lot more explanation behind this one. You need to understand exactly, what it means, what we're doing here, and what it means, kind of the proof behind it. But this is also valid. Mm-hmm. So you can first apply the sub 10. That's fine. But I was actually hoping that you would do the first one, just finding all the partitions. And then there must be 12 muffins per box. Well, same idea if you want the only partition that where all the numbers are 12, they add up to 36, sorry. It's just a 12, 12, 12, just one partition. But, you could also, and I've seen already some people doing the P12 36 3. So, that actually reduces to 1 as well. So that's fine. This would be the P36 minus 11 times 3,3, which is P33, which is 1. So you could do this as well. So this one is actually 3 and this one is actually 1. Okay, questions on this one? Okay, so as far as I've seen, for some reason, this problem was, I didn't expect this problem to be a difficult one, but I think it was. Problem number 4. So here you have 6 double chocolate. All of those 6 are identical. 6 zucchini walnut, 6 cranberry raisin, and so on. So the groups of 6, those are identical muffins. And so here, each friend must get at least 1 muffin of each kind. So you take care of the muffins separately. Mm-hmm. So here we're going to use, so I'm just going to say distribute each kind of muffin separately. So this will be identical balls, right? 6 identical muffins into that you're distributing these among 3 friends. So n equals 3, and these are different. And so this will give you, using the formula if you want, 6 minus 1, choose 3. 6 minus 1, choose 3 minus 1. So, this gives you that. That's for one kind. But there are 6 kinds, so you multiply them together. So this is for each kind, and this is the number of kinds. Mm-hmm. Okay, so in the next one, each friend gets at least 2 muffins of each kind. Well, you only have 6 double chocolates, so each friend gets 2, 2, and 2. 2, 2, and 2. Friend 1 gets 2 chocolate. There's only one way. So give 2 of each kind to each friend. That's it, right? There's no choice. All the muffins of the same kind must go to a single person. So here, the 6 muffins of the same kind become a single bowl if you want. Imagine that you have boxes of muffins, half a dozen muffins of the same kind. That's one bowl. So 6 muffins of same kind become one bowl. Okay, so now you have different bowls because you have your box of double chocolate muffins, your box of zucchini. I don't want to call them boxes, but the the double chocolate muffins, all of them, the sticks of them, that's one bowl. Then the zucchini walnut, the cranberry raisin, so all of those are different. And I have 6 boxes. I mean 6 kinds. So these are the kinds of muffins. And you're distributing among 3 friends, and they're also different. So it's different into different. And this goes for both parts, for C and for D. Okay, so all muffins of the same kind must go to a single person, no restrictions. So this is no restrictions. And in the second one, it says that each person gets at least 1 muffin. So each person gets at least 1 box of muffins. So this is no empty boxes. So each friend gets something. So this one is 3 to the 6, and this one is T63. Different to different.
Wait, so the answer for part B of 4 is just 1?
1. Mm-hmm. Right? So you have to give 2 of each kind to each of your friends, and you only have 6 of each kind. So 2, 2, 2 for each one. 2, 2, 2. Next kind, 2, 2, 2. Reasonable choice.
I'm kind of confused on the word when it says at least 2 muffins.
Yeah, that's what I was thinking.
Instead of like, it must be 2 muffins of each kind.
Well, but it's a deduction, right? If you need to give at least 2 to each one and you only have 6, it has to be 2 to each one.
Oh, 3 friends. If you distribute basically 2 for everybody, 2 double chocolate, 2 zucchini, etc., etc.
Exactly. We have friend 1, friend 2, friend 3, and here you have 2 double. Oops. I don't know. 2 double chocolate, 2 double chocolate, 2 double chocolate, right? And then that's it. And then 6 zucchini. So it has to be at least 2 per friends. It has to be 2 zucchini walnuts. 2 zucchini walnut, 2 zucchini walnut, 2 zucchini walnut. And then cranberry raisin. So same thing. 2 cranberry raisin, 2 cranberry raisin, 2 you have no choice. If I had, if you actually have dozens, it would be a very difficult problem. If you have, well, not very, very difficult, but it will be much harder.
Yeah,
if I had more, if you want another way, so that you can see you could realize that it's just 1. But if you want to use a formula, you could do the same thing that we did earlier. This idea apply here, but now you need at least 2 per friend, and we have a formula for that. We have this was this formula, and it's on the table. This formula, this 6 minus 1, this 6 minus 1 is because we do 6 minus 3 because we give one to each, and then plus 3 minus 1. It really comes from there. This is like solutions to the equation x1 plus x2 plus x3 equals 6. You have 6 muffins. This is for each kind, right? So I have 6 muffins that are identical, and I need to distribute to friend 1, friend 2, friend 3. And in my first question, it was xi greater than or equal to 1. So this formula, which is in the table just like this, comes from solving this equation. So it actually comes from this. This is the formula to solve this equation, and it reduces to that one. And this is the formula that you have in the table. But in the table, you also have the formula when each box contains at least 2. So that corresponds to x1 plus x2 plus x3 equals 6 with the xi's greater than or equal to 2. And you can see here there's only one solution. Okay, and this is per kind. But that solution looks like 6 minus 3 times 2 minus 6 minus 3 times 2 plus the separators. Choose the separators. And this is just 2 times 2, which is 1. Okay. And then you do it per kind. You're also supposed, so that's per kind, and then you raise it to the 6th power, and that gives you 1. The 6 is because, this is because we did that word per kind, number flavors. So there is like just the realization that there is only one way to do it. That's valid. Or you can use the same idea. You have this formula. You have this formula in the distributions table. I don't know which column it is that says at least this meant at least something per box. That's the one that you can use. Mm-hmm. Just apply to each flavor. So that's another possibility. Make sense? Okay. So questions here? All right. So let's go to the next one. Here. So number 5, there are 9 muffins. These muffins are actually all different, but this problem is like the poker cards problems, where you have like 4 different kinds of cards, and then you have different numbers for each of those kinds, right? So this is like 3 different kinds of muffins, and you have a small, medium, and large. That would be like the 1, 2, 3 diamonds. I don't know. Mm-hmm. So this is like that kind of problem. So here, this is a probability problem. So you're distributing these muffins to 3 friends. Each friend gets 3 muffins. Mm-hmm. So each of 3 friends gets 3 muffins at random. So the total number of cases, total number of cases for your probability. So the denominator is just 9 choose 3, 3, 3. Mm-hmm. Again, this would be like different balls into different boxes. Those are the friends. So this is n equals 9 and n equals 3. Okay. And then for the favorable cases, okay. So for the favorable cases in part A, we need each friend to get 1 small, 1 medium, and 1 large muffin. So one way that you can explain this is, you can distribute the small ones first. The small muffins. I have 3 of them, and I have friend 1, friend 2, and friend 3. How many possibilities for friend 1? 3 possibilities, right? I have 3 small muffins. And once I give that to friend 1, 2 possibilities for friend 2. And once I give that to friend 2, I only have 1 possibility for friend 3. So I have 3 factorial. And it's going to be the same for medium, and it's going to be the same for large. 3 factorial and 3 factorial. So the number of favorable cases is equal to 3 factorial q. And so the probability for this problem is just 3 factorial q over 9 choose 3, 3, 3. Part B, part B is a little bit harder, and I actually thought that maybe maybe it was the hardest part in the exam. I'm not sure, um, because see each friend gets smokings of exactly two kinds. It's actually hard to try to use something like inclusion exclusion. It gets complicated, doable but complicated. So instead, what you can do is figure out, like, what must happen. There are only a few possibilities. Let's say I have triple chocolate chip, and lemon. So I'm gonna do this. I have triple chocolate chip, and lemon. These are my flavors. Okay, and I need to have exactly two kinds for each friend, right? So one friend needs to get two of one flavor and one of another, right? Because it's exactly two kinds. So one possibility is to have one possibility. I'm just saying, okay. So one possibility is that one friend gets two triple chocolate and one chocolate, and then somebody else is going to get the other triple chocolate and some other flavor, okay, but two of another flavor. And so, if I tried chocolate, then the last one will end up with only lemon, and that's not okay because each one needs to get exactly two. But this doesn't happen. This doesn't work. So this doesn't work. The only possibility is that this one actually gets two. The one that gets the triple chocolate needs to get the lemon ones, and then the last one needs to get one lemon and two chocolate. This is the only possibility. Does that make sense? So this is in some order, you know. Maybe it's not friend one, the one that gets two triple chocolate. Maybe it's friend two or maybe it's friend three. But this is the only possibility, just in some order among F1, F2, F3. And therefore, this gives me three factorial ways to see who is the one getting the triple chocolate, the two triple chocolates and chocolate, who gets what of these three possibilities. That gives me three factorial. And then there is also, once I decided, you see, I'm separating. Here I have two triple chocolates, and here I have one triple chocolate. So I need to separate one out of the three. It could be the small, it could be the medium, or it could be the large. Okay? So there is three ways to separate the muffin. To break it like that for each flavor. So now this gives me that the number of favorable cases is 3 factorial times 3 cubed, and therefore the probability is 3 factorial times 3 cubed divided by 9 choose 3. So let me just say this is the only possible distribution, and the 3 factorial decides so that was just taking care of the favors, and then the second part is taking care of the sizes. Okay, so I thought this was the hardest problem in the exam.
What's part of the 3 to the third power for?
This the 3 to the third is taking care of the sizes. not only you need to separate two triple, you need to separate the triple chocolate ones into a group of two and a group of one. And it could be that the group of one is small and the other side large medium, or you separate the medium and then the other two, or you can separate the large and then the other two. And that's for each flavor. So that takes care of the sizes, and the 3 factorial takes care of the flavors or the different kinds of muffins. Mm-hmm. All right. Okay. Questions about that one? Okay. So, okay. So number 6, in how many ways can you distribute the 9 muffins from the previous problem that are all different into 3 identical boxes? So here I have different balls into identical boxes. And so this is my n equals 9 and n equals 3. And so these are the Stirling numbers. Stirling numbers. And so no empty boxes, that's just the single Stirling number. Empty boxes allowed, that's just the sum of these Stirling numbers, from 3 down to 1. And this is each box gets exactly 3 muffins. This is a specified number. And so for the Stirling numbers, that becomes a 9 choose 3, 3, 3. But because the boxes are identical, remember we are dividing by the multiplicities when we're talking about those types of distributions, the ones that go with the Stirling numbers. And part D was the trickiest one here. So each box gets exactly 3 muffins of 3 different sizes. So what you can do is, you have box 1, box 2, and box 3. If they were different, imagine that you have like a spot for a small, a spot for a medium, and a spot for a large muffin. Mm-hmm. For each of these boxes. So if the boxes were different, I have 3 possibilities to select the small one for box 1, 2 possibilities to select the small one for box 2, and 1 possibility for the last one. And same thing for the medium ones, and same thing for the large ones. So I'm kind of distributing distributing separately per size as I did earlier. That 3 factorial, but 3 times for each flavor. Mm-hmm. So this one is 3 factorial cubed. So I'm kind of distributing first, distributing the sizes separately. And so that would be my 3 factorial, and then raising to the 3rd power because there are 3 sizes. So this, right? And this is if the boxes were different. But since they're equal, so divide by 3 factorial. So it's 3 factorial cubed divided by 3 factorial. So this is, this is 3 factorial squared. That's 36. Okay. So everything else comes straight from the table. D requires some thinking. Questions? Okay.
Professor, are you removing any questions? Because I think it was too long. This, like, I don't know. Is there a chance, like?
Let me finish and then we'll talk about our grading. Okay?
Thank you.
So 7. In each of the following situations, find the number of ways that 27 muffins can be distributed into 3 boxes, but there must be at least 8 muffins per box. So let's see. I have 27 muffins. So I could have identical muffins. Into boxes. Actually, no, but wait. In the first one, I have identical, but they might be different or something else. So let me write pair part. So in here. So here I have identical to identical. And so instead, I'm just going to write this, the balls are the muffins, and these are the boxes. So n equals 3 are my boxes, right? And so here I have identical balls into identical boxes. And so this is a numerical partition. I'll just write here. So this is just going to be P 20 identical, 27. Oh, wait. P8. So this is my restriction. At least 8 muffins per box. So I have numerical partitions, but with that additional property. So, oops. 3. And now we need to simplify that. Okay? So P8, 27, 3. And I know that I can reduce this by subtracting 7 times 3. So 8 minus 1 times the second part. So 7 times 3, comma 3. And so this is P 6, 3. And I have different into identical, different balls into identical boxes, which means that it's going to be multinomials. But because I have that extra condition that there are at least 8 muffins per box, I need to find the partitions. So the specified partitions with, for the condition at least 8 muffins per box are, I need to have 8. So the next one could be 8, and they need to add up to 27. So I have 16. So 8, 8, 11. Mm-hmm. Another partition is 8, 9, 10. 19 and 8, 10. And there's one more partition. If I still have 9, 9 and 9, 1, 9, 9, 9. So those are all my partitions. And I'm going to use those partitions in several parts. So here, because this is different into identical, so this is like the equivalent to the T numbers, not the T numbers, but the S numbers, the Stirling numbers. Mm-hmm. And for those, what I need to do is the multinomials. So 27, 8, 8, 11, 27, 8, 9, 10, and 27, 9, 9, 9. But because this is like the equivalent to the Stirling numbers, but with a specified number of balls per box, I need to divide by the multiplicities. So 1 over 2 factorial. Here I don't have, all my multiplicities are 1, so I don't need to write anything. And here I need to divide by 3 factorial. And since we already have the partitions, I'll do D first. So I have different into different. So this is the equivalent to the T numbers, the first row in my distributions table. So again, I'm going to use the the same multinomials, but this time I need to multiply times all the rearrangements of the numbers in my partition. So for this one, it's 3 factorial over 2 factorial. And those are just the rearrangements of 8, 8, 11. 3 factorial divided by 2 factorial because I have 2 8s. And then and this one there's no need because in this one there's going to be 3 factorial over 1 factorial times 1 factorial times 1 factorial, so 3 factorial. And in the last one, so that's just the one. But if you want to know, like, I'm gonna write it in black. This you don't need to actually write. But that's really what's going on. You are writing the number of rearrangements of 8, 9, 10 right here.
Sorry. Question: why is part C skipped?
Oh, because these two are similar, so I just wanted to do D first.
Okay.
It's similar. And then for part C is a direct application. You have a formula identical into different. You have a formula. This is also if you want, solutions to integer solutions on equation x1 plus x2 plus x3 equals 27, so that I write it like this: x1 plus x2 plus x3 equals 27, so that all the xi's are greater than or equal to a, and they're integers. But you also have a formula in the table, so there's no need to write it as solutions to that equation. But that's a possibility. So 27 minus 8 times 3 plus the number of separators.
One other question.
Yeah.
If problem B of problem 7 says the muffins are different and the boxes are identical, then shouldn't this not be a partition? Because and this one too, because 8A and 999 are the same number of muffins. Like
yeah. So these partitions, if you want, should actually be here. This P63 is actually 3, and those are the 3 partitions. So you could have done it. You could have done it like this, or you could have found this. In fact, you say, let me move it if you want. But I actually found them later because you need them for the other problems. So you don't really need them in the solution of problem 1. You don't really need them, but let's do this. Oops. You don't really need them in problem 1, but you need them in the other 2 problems. You see? So let me say it like this.
Oh, okay. If that answers for part A, not part B, then I got confused then.
So that's what I'm saying, and that's why I'm moving it. You don't need to write this here if you don't want. Okay? It's not, finding those you can think of as finding the solution to problem A, but it's not necessary anyways. In problem A, you could use the formula and just get the 3, but you could also, figure out how many, and that's your answer, right? So you have 2 possibilities for part A, but then for parts B and D, you need to know what goes on the bottom part of the multinomial. You need it. And therefore, even if you didn't do part A this way, you're going to need to find those triples in order to be able to solve that problem. That's why I originally wrote it here, because you need them here. But you're right. If I'm asking for the partitions, for the number of partitions, this is the answer. Then 3 partitions, and this is the actual partition to part A. But in order to solve B and D, I need to know what are all the partitions. This is essentially what we write in the summation in the table. you know that for these parts, you have some summation of multinomials. And those multinomials need to be these triples. That's exactly what's happening. So
yeah, or unless I'm mistaken on the meaning of different, because I was thinking different number of partitions. Like in each box, you cannot have the same number of muffins in each box, or in each box it has to be like 8 muffins, 9 muffins, and
10 muffins.
10 muffins. So I thought that was the only partition for 27 muffins.
Oh, no.
Or,
What is different is if the muffins are all different. No? The muffins are all different, but it's not telling you anything about the sizes of the parts. The only thing that you're given about the sizes of the parts is this, that they need to be 8 or more. That's all. Make sense?
I suppose.
Mm-hmm. Okay, you can review it. I know it's a lot to take. Plus, we just had the break, so. But you can review it and let me know if you see something that doesn't make sense. And so, finally, for the last problem, a combinatorial proof. So we just need to count two things in the same way. So what we're going to count is the number of ways. If you look at your table, you have one of the formulas is exactly this one. This is the formula for the number of distributions of m identical balls. So here I'm going to say muffins into n different boxes and with no restrictions. Just that. Okay? So the left-hand side is just that formula for that problem. Identical into n different, no restrictions. That's just that. Mm-hmm. So that's the formula that we have on the table. On the other hand, you can divide into cases according to how many empty boxes you allow. So here, when I say no restrictions, you know, in other words, I'm saying that empty boxes are allowed. So here I'm going to divide into the number of cases according to the number of boxes actually used. So, or if you want the number of empty boxes. But so that it looks like my formula, I'm just going to say we can use any number of boxes k between 1 and n, right? I have n boxes. So I can use 1 or 2 or 3 or 4 or all the way to n. And therefore, there are, for each k, there are, I choose k to select the boxes being used. Mm-hmm. And then there are n minus 1 and k minus 1 ways to distribute the m identical muffins into those n, oh, not n, but k different boxes. For a total of h is k and minus 1, k minus 1 distributions for each k. Therefore, there are just a sum. And that's it. Okay, any questions? Okay, so that's the exam. What I'm doing is the exam is worth, I'm grading out of 100 points. I declared as 100 points, but there's actually 115 points. So there's 15 extra points. So instead of removing a particular problem, which wouldn't refer to those who tried that problem, it is actually worth 115 points. There are 15 extra credit points, which in my mind essentially covers that, the part that I told you that was the most difficult one in the exam, which I had that in purpose as the most difficult one. And so that's that. Any questions?
Would the next exam have less problems? I felt like it was a lot of parts to this to finish in the amount of time we have.
Well, we finish in the amount of time that we have right now, and I actually have more than one solution per problem, and plus it's 115 points, so I think it was okay. There's one more thing, which is that I don't know if you remember from the syllabus that the lowest of your exam, the lowest grade on your exams counts less than the other two exams. So, that's another thing that you should take into consideration.
Professor, just so I'm understanding you correctly, so the total amount of points that you can get on this test are 115, but it's graded out of 100 points. So if you got, let's say 80 points out of a possible 115, that would count as an 80% final grade.
Yes. Yeah, and if you get 115, then you have 15 extra points for something. Yeah. Or let's say you don't have a perfect exam, but you have 100 points total, then it counts as a perfect exam. Mm-hmm. Yeah. So, you can ask me more questions whenever you want. You can, take a look, see if there's any other questions. We do not have a final exam, so we won't have anything very similar to this. But you know that we kind of everything that we learn kind of is used for future things. So that's the way that you will continue using these techniques. Okay.
Professor, about your office hours, I have a class from 2 to 3:15 every Tuesday, Thursday. Is there another time I can meet with you?
Just, whenever you need to see me, let me know, and then we can try and find a different time.
Okay, thank you.
Okay. All right. So, in the last 10 minutes, let me just remind you what we were doing before, so that all the problems that I am assigning from section E will be extra credits. So if you're interested, let me know. I will have the list of problems for that section available between today and Thursday, and then you can let me know on Thursday if you're interested in providing a solution on a wiki for that. Those will be extra credit. If you, I'm hoping that by then you'll have your exam results. If you did really well on the exam, maybe leave those extra credit problems for other people. If even though you can take them if you want, but I would suggest. And then if you didn't do well in the exam, I would suggest you take one of those problems right away. Okay. So we were doing inclusion and exclusion, which was essentially, we went over one of the solutions today. Use inclusion and exclusion. I won't write the formula again, but let me just, instead of rewriting something, this is what we were doing before. The idea is that you need to, you subtract from the total, but you're subtracting more than you should, then you need to add, and then you subtract, and then you add. So it was that idea. But I just want to show you one application, hopefully, one quick application of that, and then we'll continue on Thursday. So, here's one possibility. A derangement, we skip this from section A because it actually goes together with this section. So a derangement is just a rearrangement of a string with different elements. So that no element occupies its original position. Okay, so for example, if I give you the string xy, and then I look at all its, all the permutations of the letters, all its rearrangements, you have xy and yx, right? Those are like all the permutations. But I do not want this one because here the x is staying in its original position, also the y. So that one doesn't count. So there is only one derangement. So these are all rearrangements, but only one of them is a derangement. Okay? So let's do 3 letters at a time, A, B, C. Okay? So I can write the 3 factorial. That's all the ABC, ACB, BCA, BAC, BCA, CB, CAB, CBA. That's it. Mm-hmm. But many of these fail to be derangements because, here the A is in its original position, here the B is in its original position, and here the C is in its original position. So all of those fail, and some of them for more than one reason. Mm-hmm. So the only derangements are, BCA and CAB. Okay. Now, one more definition. It gets more complicated, right? And in fact, you are asked to find the number of differentials for very small numbers in section 8. But it gets very complicated. So I'm just going to say that the n is the number of derangements of a string of n different elements. And it doesn't really matter what the elements are, right? So I could have used XYZ here, or 1, 2, 3, or any other thing. Mm-hmm. So here, what we did was we found out that D2 is 1 and D3 is 2. Mm-hmm. Well, it happens that there's a formula for the number of derangements. So I'm just going to call it theorem, and we're going to prove it next time. The number of derangements is n factorial times the sum from k equals 0 to n of negative 1 to the k over k factorial. Does this look familiar to you? Just a summation. Forget about the n factorial. Does this remind you of something from calculus? Well, we'll see it next time. But we're gonna prove this using the inclusion-exclusion principle. But what I'd like you to do from today to Thursday is, think a little bit about it. What would be your sets? Try to remind yourselves of the notation that we have. What would be your set AI? You're trying to make your sets whatever you want to exclude. Okay, so I'll continue right here. And the other thing that I'd like you to check is that D4, if you substitute in this formula, it should give you 9. So check that it is actually 9 and find. So this is like a small exercise for you, just to, understand what's going on and you're ready for next class. So check that D4 is 9 and find all 9 derangements of, let's say, the string 1, 2, 3, 4. Okay, so I'm using numbers because we're gonna use that in my proof. But I could have used A, B, C, D or X, Y, Z, W or whatever. These are my 4 letters: 1, 2, 3, 4. Right? Do you understand this exercise? This is just like a warm-up so that when I go over the proof, you are familiar with what we're doing. Okay? And then there are a few problems on derangements on section A that we're going to go back to, and several ones on section E. So I'll have that included in my list. So, it would be good that you familiarize with them so that you can pick some of those extra credit problems. All right? Questions?
I have a question about the not about the subject, but about the wiki problems. So if someone has a question about the subjects, I can wait.
Okay. Any other question? Okay, guys. So feel free to go. It's 12:15, so class is over. If you have any questions, then let me know. Anything else?
So, Professor, you said the extra credit includes something about these exam questions?
No. It's not about the exam questions. So I'm gonna have extra credit problems for section E, and
Okay.
I'll have them available on Thursday.
Okay.
Okay. So let me just here. So extra credit, wiki problems. That's going to be all of section E is going to be extra credit. Although, as always, think of these problems as assigned to everyone. So, you should try them regardless of, whether you provide an official solution to the wiki or not. And just my other reminder is my office hours are going to be 2 to 2:45.
And I'm guessing the office hours link is still the same.
Yeah, the days are Tuesday, Thursday, same as before.
But I didn't mean the day. I just meant the same link ID.
Oh yeah, yes. Thank you, Sean. Yeah, it's the same link, the same everything. I just moved them half an hour because I never get lunch, so I need a little bit of time in between because I teach all morning.
Okay.
Okay. All right.
And I'll probably would like to try and do a wiki prompt because based on the looking at the solutions of the thing, I did a lot worse than I thought I initially did. Because even the problems that I thought, okay, I probably got that one wrong, but I think I got this one right, and now I'm thinking, yeah, I got it totally wrong. Like the ones that distribute 36 muffins into 3 identical boxes. I think I just left it partition sub 12 of 36,3 when it should have been just one possible way, but I didn't realize it at the time.
Oh, that's okay. If your formula, it's okay. That's fine. You don't need to get to that one.
The instructions said that we weren't supposed to leave it like that. We were supposed to simplify it, but I didn't know how to simplify those annoying partition formula stuff.
Yeah, there's question. But wait until you see your exam, okay?
Yeah, so at least now I have a better idea, but yeah, it was a very difficult exam.
Okay.
Let's see.
Okay, don't worry, Sean. Wait until you see your exam.
Okay.
Noah, how about your question?
My question was just about the wiki problems. You said they're going to go up between today and Thursday, and we should let you know on Thursday whether we want to do them or not?
No, they're not going to go up between today and Thursday. I'll decide on those, and I'll have them ready on Thursday. Okay? So whenever I upload them or I decide on the list, I will let everyone know. I'll send a message. But I'll give some time, for people to actually propose or volunteer for them. So I'm just trying to figure out a way to be fair, but everybody will find out at the same time. Okay?
Thank you, Professor.
All right. I'll see you, Noah. Anything else?
Oh, one person pointed out how much points can we get for doing these extra credit wiki problems?
I'll let you know. I'll let you know when I have the list. I'll have the number of points per program. Okay? Because there are some that are much easier than